everybody. We're back with Chapter 5, which is where we begin our journey on continuous random variables. So we've seen it all now. We've seen discrete random variables with, the generic probability distributions and, binomial distributions. Today, we will see for the first time what happens when we look at continuous random variables under those circumstances, I suppose. So, what exactly are we doing tonight? Well, we got continuous probability distributions, so I'll be giving you just, background info on those. And the uniform distribution, which is a rectangular shaped probability distribution. A little bit funky, but that is sort of a fun one. I actually quite enjoy that one. And then we get to the meat and potatoes part of the lecture, which is going to be the normal probability distribution, which we've seen before. That's the one that looks like our bell curve. And then the cumulative normal table, and that's a new thing for us. And then we'll be approximating the binomial distribution by using the normal distribution. So, very important. And then a small little topic at the end, the exponential distribution. It's sort of, it's related to the Poisson distribution. We cover it, but we don't cover it in great depth. Okay, some fill in the blank. So get your notes and fill away with me. And here we go. So a continuous random variable may assume any, not confident that worked, we'll assume any numerical value. So any numerical value in one or more intervals. That is part of a continuous random variable. We use a continuous probability distribution to assign probabilities to intervals of those values. Many business measures like sales, investments, costs, revenue can be represented by continuous random variables. And here's another name for it, a probability density function. I like using that phrase. So what are some properties of these continuous probability distributions? Well, if you haven't seen this before, it's just the math way of writing a function. So properties of, we read this f of x. F of x. That's how you read it. So f of x is a continuous function such that the entire function is greater than or equal to 0 for all x. The total area under the curve of f of x is equal. And this is an essential point, and you've heard this one before for probabilities. An area under a continuous probability distribution is a probability that's equal to 1. Okay, so it's got to be a probability equal to 1. And you know that for probability that seems to be always the case. So what does this thing look like? Words are great, but pictures are much better. So this is what that probability distribution looks like. So we are indeed just talking about our bell curve. And the blue colored area under the probability curve, f of x, from the value of x equal a down here to x equal b over here, that's the probability that x could take any value in the range of a to b. Okay, so you got your probability curve here, and then if you define two values on the curve and you calculate the area from one to the other one underneath the curve, then that's going to give you the probability that x is going to land between a and b. Okay, now, generally this involves calculus to calculate areas under curves. The good news is that we have some fancy formulas and stats that do a lot of the work for us. So you'll get used to notations like this in this lesson, and we will just move along. A couple different distribution shapes. We can have symmetrical and rectangular. That's the uniform distribution that we're going to be looking at in just a moment. We can have symmetrical and bell shaped. That's the normal distribution that we'll be talking about later. And then we have already seen examples of skewed distributions that are either left or right. So here is the uniform probability curve. So this is the one that I said is looks like a rectangular distribution. Now, this fill in the blank's already done for us, but the rectangular distribution occurs when probabilities on a continuous interval all have an equal likelihood of occurring. So if any point on the distribution has an equal likelihood of occurring, you have yourself a rectangular distribution. Looks like this. Now, ignore all the shading. The shading is just, I grabbed this from like an example, but this is what they might look like. And we can keep going here. So, a little bit about the formulas for a rectangular distribution. If C and D are numbers on the real line, that's just saying like the real number line, so it can be continuous. So it could be numbers like 1.2 or 1 or 2, whatever. C being less than D, so just saying C smaller than D. The probability curve describing the uniform distribution is this one right here. Now, this will be, I believe, on your formula sheet. So this just means f of x is equal to 1 over d minus c, and just stipulating that c is less than whatever x you're looking for, which is less than d. So basically you're on the interval somewhere. And this is your probability, okay? Otherwise it's 0. So if you're not falling between c and d, probability is 0. So that just means you've moved outside of the distribution and there's no probability there for you. The probability that x has any value between the given values a and b, where a is less than b, is given as such. So we write it like this, and this just means that if you look at it like visually, x is in between a and b. If you read it mathematically, we actually read it starting from the middle, and you go this way, and you say x is greater than or equal to a, right? We're reading it this way. And then you read it this way, and you say x is also less than or equal to b. So it's just a fancy way of saying that x is in between those two numbers. Now our formula becomes this, so we go b minus a, that's the end point, minus the start point over the entire distribution, okay? Right, the mean and the standard deviation of a uniform distribution are as such, and yeah, they look a little weird, but you know, that's the way they are, okay? So you'll have those formulas on your formula sheet, and we're not going to really get into like why it is the way it is. Got a couple of fill in the blanks here. So notes on the uniform distribution. The uniform distribution is symmetrical. And where is it symmetrical? Well, it's symmetrical around its center, which we know that the center of something is usually the mean or the median in some cases. So here's, you know, a rectangle, and if you're in the center, then it's clear that it's symmetrical, right? You got the same amount to the left as you have to the right. U of x is also the median. And if you think about the way a rectangle is, if you're in the middle, it kind of makes sense that that's the mean and the median. The uniform distribution is rectangular, which we said already, but it doesn't hurt to say again. And for endpoints C and D, or C is less than D and C doesn't actually equal D, the width of the distribution is D minus C. Now, if you think about that for a second, if I say, hey, I got my rectangle, and let's just call this bottom corner 0, and we'll call this corner 6 units, okay? What's the length of this side? Well, if you call this D and you call this C, then it makes sense the length is D minus C, or 6 minus 0, 6 units, okay? And the height is 1 over D minus C. Well, the height for a probability distribution, that's gonna be the actual probability. Okay? So that's gonna be that's gonna depend on the actual distribution itself. So it's not gonna be the same thing every time. So it's 1 over D minus C. The area under the entire uniform distribution is 1. So if you calculate the area of the rectangle by going the length times the height, you should always get 1. All right. We're going to do this example, this elevator waiting time example, just to demonstrate it, because although these are sort of straightforward to calculate, it's kind of hard to understand without an example. At least if you're me, that's the case. So, in this example, the amount of time x that a randomly selected hotel patron waits for an elevator is uniformly distributed between 0 and 4 minutes. Okay? So you're standing there, you press the button, and you're going to wait somewhere between 0 and 4 minutes for that elevator. Perfect. So, C is going to be 0 and D is going to be 4. Now, if you go and use those formulas that we were talking about before, right, the 1 over D minus C, then we can see that there's a 1/4 chance. Okay, so 1 over 4 minus 0 gives you 1/4, otherwise it's 0. Okay, so because it's a uniform distribution, at any given point, there's a 1/4 chance that you're going to wait, say, between 0 and 1 minutes, or 1 and 2 minutes, 2 and 3, and 3 and 4 minutes. If you add them all up, you get 1. If you move outside of the 4 minutes, then the probability is 0, because it never takes more than 4 minutes. Now, this here is just me preloading that formula from before, that if you're going to calculate some probability between two given times, so let's say whatever, 1 minute and 2 minutes, then I'm going to use this formula. Okay? Here it is. I think this is where it really makes a bit more sense. So here's the picture of the distribution, by the way. So remember, this is 1 over d minus c. This is c. This is d. So 1/4 chance of waiting any amount of time. Here's the probability distribution from 0 to 4, and it's uniform, so it's rectangular. Okay, what is the probability that a randomly selected hotel patron waits at least 2.5 minutes for an elevator? Well, we just need to calculate the area under the curve from 2.5 minutes to 4 minutes. We don't need to go past 4 because the distribution doesn't exist. And now it is asking for probability that x is greater than or equal to 2.5, right? So the max is 4. So if I can just calculate this probability, then I'll have the answer. Well, if you just stop for a second and use, your knowledge of rectangles and calculating areas of rectangles, you know that to figure out this length, you're going to go 4 minus 2.5, right? And that'll be like, oh, okay, so that's 1.5. And then what's the height of the rectangle? Well, the height of the rectangle is 1/4. So really, all you need to do is 1.5 times 1/4, and you will have your answer. So if you do that, you're going to get 0.375, or 37.5%. So there's a 37.5% chance that you'll wait at least 2.5 minutes. All right. What is the probability that a randomly selected hotel patron waits less than 1 minute for an elevator? So really what we're asking for is probability that x is less than 1, which really is like asking me, from here to 0. So I'm just finding this area this time. So another way that you could write this, it's really like asking what's the probability that x is going to be between 0 and 1. Now we do have our formula that we can use, which is this one from before, right? B minus A, and this is A, and this is B. So if you want to use the formula, you can. A lot of students, so that's A, that's B, and we know that it's B minus A over D minus C. That's the formula from before. So let's use that this time. You go 1 minus 0, and then D is 4, and C is 0. So you get 1/4, or 0.25, or 25%. Now, what if you just use the picture? Well, the picture means you're finding the area. So length of 1, height of 1/4, 1 times 1/4 is still just 1/4. So no matter how you do these questions, I think drawing a picture really, really helps for uniform distributions. If you don't want to draw the picture, you can use the formulas without drawing the picture. So it's kind of up to you. And that is basically the uniform distribution. One last thing. It wouldn't be complete if we didn't calculate the waiting time, the mean waiting time. Now, you're not going to be surprised what it's going to be in this one, because the mean waiting time, remember, is the midpoint of the distribution. So it should be 2. Now, the formula I gave you is this one right here. It is C plus D divided by 2. And in our case, well, I guess I'll go down here. C is 0, D is 4 divided by 2. So your mean is 4 divided by 2, or 2 minutes. There. Standard deviation. So the formula is D minus C over the square root of 12, which I know is odd. There's a reason for it. It's just we're not going to cover it. That's not the point of our course. So here we go. Plugging that in. What do you get? 1.1547. Don't forget the units. You don't want to lose marks for that. There. Perfect. So that's uniform distribution. That's as far as we go. And now we get to the meat and potatoes part. So, normal distribution. The normal probability distribution. Don't know why I keep losing my draw with touch. It's very annoying. Okay. The normal curve is symmetrical around its mean and bell-shaped. Well, we knew that because we've seen it before. Mu is also the median. The tails of the normal distribution, extend to infinity in both directions. So here's our normal distribution, and it looks like our tails end, but in reality, they keep going on and on and on and on forever and ever and ever and ever. And that's like a very small detail that's important when you really start zooming in on things. So, tail gets closer to the horizontal axis, meaning the x-axis, and never quite touch it. So basically, the probability never quite goes to 0, but it approaches 0. The area under the entire normal curve is, can you guess it? Anyone? It's 1. That we know from probability. That's always seems to be the case. The area under either half of the curve is 0.5. Great. So what I'm trying to impress upon you is that this is symmetrical curve. And if you read the picture, that's what it says. What are some properties of the normal distribution? So there's an infinite number of possible normal curves, and they're all based on a different mean and a different standard deviation. Okay. So basically what I'm saying is, I can create, anything that has a mean and a standard deviation, and is approximately normal, right? Follows that, remember that rule, what is it, the 68, 95, 99 rule, right? Then it's a normal distribution. So, the particular shape of any individual normal depends on its specific mean and standard deviation. The highest point of the curve is located over the mean. Don't know why I shouted that. But if you got a normal distribution, then whatever the highest point is, that's the mean. The mean is equal to the median is equal to the mode, right? That's for a perfect normal distribution. All the measures of central tendency equal each other. And there is the only probability distribution for which it is true. Right, now, the only probability for which all three mean, median, and mode equal each other are for the normal distribution. So it is a very special distribution. All right, let's talk about normal probability. So how do we use these things to calculate probabilities? Well. Suppose x is normally distributed random variable with a mean of mu and a standard deviation of sigma. The probability that x could take any value in the range between two given values a and b, such that a is less than b, is denoted like this and drawn like this. So there it is. Perfect. I feel like we've said this. Now, what is the formula for this? Now, we've actually seen this formula before, because we did a little bit sort of in the first week or so. A second week rather. If x is normally distributed with a mean of mu and a standard deviation of sigma, then the random variable z, you'll remember that one, is described by this formula. And it's already on your formula sheet. So it's x minus mu over sigma. Now remember, we were using this to find z scores. And I said this is a way of mapping some random variable x, converting it to how many standard deviations above or below the mean we are, and giving it a number. Okay? So right here, where you have your mean, that was a z-score of 0. Right? So if your x is exactly equal to your mean, it means you're 0 standard deviations above or below the mean. If you had a z-score of 1, then you were over here. And if you had a z-score of -1, then you were over here on the left. And if you go 1 standard deviation to the right of the mean and 1 standard deviation to the left for a normal distribution, that was capturing 68% of your data. Okay? All right. So that's just sort of a recap. I think I'm going to go into that a little bit more. The standard normal distribution. So Z measures the number of standard deviations that X is from the mean mu. That's what we were just talking about. Okay, so this is very important. So it's an easy enough concept, but it's very hard to really understand, I think. It took me like, it really took me a few years before I really understood. And the whole time I thought I understood. It wasn't until later that I was like, I kind of did, but not really. So, the algebraic sign on Z indicates which side of mu that you're on. Okay, so here's your standard, or here's your normal distribution. Okay, and remember, the center, the exact center, is the mean. Now, if you go the mean plus your standard deviation and the mean minus your standard deviation, then you got 68% of your data. Remember, if you go 2 standard deviations out, then you got approximately 95, and then if you go 3, see we get pretty close to the end, then you got about 99. Okay. Now, as far as the z-score goes, that's a z-score of 0 for being right in the center. And as we move to the right, 1 standard deviation above the mean, 2 standard deviations above the mean, 3 standard deviations above the mean. And if they're negative, then you're just below. All right. How do we use this to solve questions, I suppose, or calculate probabilities is what I should really say? Well, here's the general procedure. So I'll give you a moment. Like, you might want to pause the video here and just read through it. I suppose I could do it too, but you might want to pause. But yeah, you'll calculate the z-score for each value. So let's just say you're trying to find like a mean that's between two points, A and B. So you calculate the z-score for each one. Now, there's a table that I'm going to show you in a moment where someone has calculated a bunch of the probabilities under the curve for us. So remember when I said you need calculus normally to solve these kinds of problems? Well, as long as we have our probability table, we don't need calculus. We can actually look up the area on the table. Okay? Once you have those two areas, you're going to subtract the small area from the large area, basically, and then you'll be finding the shaded in blue part. And I really, really recommend this thing in red. Always draw a picture to help place your numbers on there, and you're going to be way less prone to making weird mistakes. Okay? So, let's see. Here's a question. I will just show you probability table. So this is, on Moodle, and someone has gone and calculated all the probabilities for a bunch of z-scores. Over here, you'll see that the table gives the value, it gives the area under the curve to the left of the z-score. That's why it's shading in to the left. So if I have a z-score here, then it's finding the area to the left. This is how the table works. Let's say I have a z-score of exactly 0. So the left-hand column tells you the first decimal, or the first part of the number, I should say. And then up at the top, the columns give you the second decimal, if you have it. So for a z-score of 0, I go to 0.0, and then I look up here and I go to 0.00, so that's the second decimal, and you'll see that where those two things line up, that's 50%. My z-score of 0 should be 50% of the curve. That we know. If I have a z-score of 1.0, then I just need to look here, and I'm already in the 0 column here, so that would be 0.8413% of the curve. Let's say you got a z-score like, I don't know, 1.24. So find 1.2. And then you go over until you find the 0.04 column. So that's right here. It's a little bit tricky. There. Now where those two lines cross, 0.8925, that would be a z-score of 1.24. Okay? So let's go ahead and try a question. A coffee temperature question. All right. What is the probability that the temperature of a randomly purchased cup of coffee will be between the requirements of 67 and 75 degrees? Now, most coffee chains have quality control things like this, and they have instruments that make sure that their coffee comes out at a certain temperature. Believe it or not, I can attest to this. So, let x be a random variable of coffee temperatures in degrees Celsius, and basically what we're trying to find is the probability that our random variable x is somewhere between 67 and 75 degrees. Now, given that it's normally distributed, so they have to say that you can't just willy-nilly apply the normal distribution. You have to know it's a normal distribution or be told it's a normal distribution if it's a question. So, as long as it says it's normally distributed, now they're giving us the mean and the standard deviation. You'll notice that the letters are not sigma and mu. That's because this is a sample. Okay, we still use the same formula. So, let us move along. and figure this out. Here we go. So you need to figure out, because we're trying to figure out probability that it's between 67 and 75. Now, we're going to be using this formula here, that z equals x minus mu over sigma. So for 67 degrees, what's the corresponding z value? Well, z equals x minus mu over sigma. Now plug in your numbers. This is x, so you go 67 minus the mean, which was, I need to remind myself here, kind of an annoying number, but 71.1574. We're getting real precise. Divided by, now remember, we're just going to use the sample standard deviation, 3.1495. Now, plug that in on your calculator, and you will get, pause the video here, negative 1.32. There's no point doing more than 2 decimals for a z-score because our table only goes to 2 decimals, by the way. All right. So what have we found here? Normal distribution. Here's the mean, which in this case is 71.1574, and we just found a z-score of negative 1.32. So it just means that this temperature of 67 is 1.32 standard deviations below the mean. Okay, so it's like somewhere over here. All right. Same thing for x equals 75. We're going to use the same formula, but this time I'm just going to plug it directly into the formula and write it out. Okay, now pause it here for a moment, get your answer, plug it in, 1.22. So this temperature is clearly above the mean, and it's 1.22 standard deviations above. So what exactly are we doing here? This is where I say it's really important when you can, which is all the time, to draw a picture. So here is my standard deviation again, or sorry, my normal distribution. It looks ugly, but there it is. Now I like to just plop roughly in the center the mean, and I can plot my 2 z-scores on here. So one of them is above 1.22. The other one is below, because it's negative. So z equals negative 1.32. Okay, now my random variable x, so this represents the temperature of 67. This represents the temperature of 75. And I'm looking for the probability that x is between those 2 numbers. So because it's a normal distribution, we actually know that if we can calculate this area under the normal distribution curve, we will have the actual corresponding probability. Oh, that's pretty neat. So how do we write that in math? Well, we already wrote that the probability that x is between 67 and 75, so that's how you write that part. Now we're going to write, well, it's equal to the probability that x is less than 75 minus the probability that x is less than 67. Now, why? Well, let's look at our picture here for a second. Use a different color. Remember, this is 67. Our table only gives us the value to the left of every z-score. So if I want to find this middle part, then I look up this score here, but that's going to give me from here all the way there. Okay, so it's going to give me the big green area. So that would be the probability that x is less than 75. The table gives the area to the left. I want the shaded part. So I need to then go and look up the probability that x is less than 67, which is this part. Right? So if I can go the green area, which represents the whole thing, and I remove the black area, what are you left with? Well, you'll be left with just this part. Okay? So that's why we write it like this. And that's why we, I suppose, do it that way. Now, at a certain point, we stop writing the numbers with x and we say, well, we're looking at the normal distribution. So we use the formula to calculate the corresponding z value. So then we say, all right, well, this one is actually the z score for less than 1.22, which you can look up on the table. And this one is the z score for less than negative 1.32. Perfect. Let's go look these numbers up on our table. So first we'll look up the big one, which is 1.22. So z equals 1.22, so find 1.2, and then move over to the 0.02 column, so that's the third one in. And we find 0.8888. So remember that number. Or better yet, write it down. Did I lose my pen again? No, I didn't. So this is 0.8888. All right. Then go look up negative 1.32 on your table. We'll go for negative 1.32. So go find negative 1.3. And then, oh, thank goodness we can see it this time. There we go. So it's 0.0934. So you can write 0.0934. I'm amazed I remembered that. There we go. Do the math, and you're going to get 0.7954. Or if you multiply by 100, that's 79.54%. So, with the data they gave us, and you should write sort of a concluding sentence, there's a 79.54% chance of the coffee temperature being in the correct range. There you go. Perfect. I happen to know a franchisee who owns a coffee chain, and their corporate office will send out random people to get coffees and test. That's one of the things they'll test is, does it come out at the right temperature? So let's order black coffee, and this person has to go and make sure that every week or something like that, they recalibrate their machines. So they have some very specific ways that they measure the temperature and make sure that the machines don't need to be adjusted. Because as you know, wear and tear on the machines over time can make it too hot or too cold. Yeah, so this is like real world stuff, man. All right. What if we have to find a point where z is greater than a value on a standard normal curve? Well, the good news is that our table gives the area to the left. And keep in mind, and by the way, actually, not every table gives the value to the left. Some tables give the value to the right, but our table, the one you'll always have with you, gives the value to the left. I think that this makes it easier. Now, all right, go away, box. Okay, this represents the probability that z is less than a value, right? So if we're going to the left, we're always looking to the z less than the value. If you need to find the probability that z is greater than the value, well, then just use that handy fact that all probabilities have to equal 1. So you simply subtract whatever value you look up on your table from 1. So here's like a picture and an example. Find the area under the curve for a z value of 2. Okay, so for a z value of 2, if you look it up, we won't spend the time, but you get 0.9772. You can confirm it yourself. Okay, what if I want to find the area that's to the left of that value? Well, you're not going to find it on your table. So your table only gives you to the left. I should have said to the right. Okay, so if you want to find the area to the right, then what do you got to do? So you look up the value to the left, which is 0.9722. And then you go 1, subtract that value, and you'll be left with a tiny piece over here, 0.0228. Well, that's nifty. Let's do a question. Ah, yes, one of my favorite questions. So example of finding areas to the left of the z-score. If my kitty's weekly puking patterns are approximately normally distributed, with a mean of 12 pukes per week, with a standard deviation of 7 pukes per week, find the probability that a kitty will puke more than 18 times per week. This is a true story. I had a cat that used to puke, if it puked, it would puke in 15 different places in the space of a minute. It would just run around the house puking. It was a nightmare. Needless to say, that cat is no longer with us. So, what are we going to do? What are we going to do? Well, it says it's normally distributed, so we can go ahead and use our fancy formula, this one. We're going to go ahead and find a z-score. So I'm looking for probability that x is greater than 18. So let's see. They say the mean is 12 and that the standard deviation is 7, and then my x value is going to be 18, right? Plug it into my little formula here. So we go 18 minus the mean of 12 divided by the standard deviation of 7. And I ran out of room, so I'm just going to go like this. What are you going to get? Well, on the top, you're going to get 6 divided by 7, which gives you 0.86. All right. Now, remember, on the table, so on the z-score table, we can find probability that z is less than 0.86 because our normal distribution table always gives us the value to the left. So here's the mean of 12. Okay, now I was asking for an x of 18, which is clearly above the mean. So this is a z-score of 0, and this is the z-score I calculated of 0.86. Now, if the question was asking less than 18 times per week, I would be wanting this area, which I could just look up on the table. But that's not what the question's asking for, right? The question would like to know, what's the probability that it's more than this? Well, that represents this area of the curve, okay? So what we need to find here is the probability that z is actually greater than the score we found, 0.86. Well, I know that if I want to find the area to the right of a score, I just need to go 1 minus the probability that z is less than that value, which I can get from the table. So let's go to our table, look up 0.8, there it is, and scroll over until you get the 0.06 column, so that's this one here. There it is, looks like 0.8051. Perfect. So 1 minus 0.8051. Do the math. Type it in on your calculator like me. I'm not going to mess around with those decimals. There you go. What was this? This was the probability that x is greater than 18. Okay. Write a concluding statement that there is a 19.49% chance that the kitties will puke more than 18 times in a week. Wow. All right. Let's go ahead and reverse look up values of z to find the value of x. So I call this a reverse question because in this question, or in these types of questions, we actually know the probability that we're looking for, and we want to go and figure out the actual x. Okay, so sometimes we know what the given probability we want to achieve. We need to work backwards to find the given x score. So here we go. A large discount store sells 50 packs, you can tell this is an old question, of HX150 blank DVDs. Okay, remember back in the days, anyone old enough to remember when you actually used to go buy rewritable DVDs? Because it was a way, USB sticks still weren't a thing. So the weekly demand is normally distributed with a mean of 100 packs and a standard deviation of 10 packs. Okay, so normally they sell 100 packs and plus or minus 10. How many 50 packs should be stocked at the beginning of a week so there's only a 2.5% chance that the store will run short during the week? We will let x equal the number of 50 packs that will be stocked. So the x value must be chosen so that, well, let's do some thinking here. What do we need to do? Let's go back to my blue. So what do we need? Well, we need the probability that the z-score is actually greater than some given number, right? Where that number, I don't know if I'm going to write this out, where that number represents the value, it's going to be a slow reveal, where that number represents the value of the normal curve. That is, let's see, only a 2.5% chance the store is going to run short. So 100% minus 2.5%, or 97.5% of the curve. Wonderful. So here's my normal distribution. Here's the 50% line. Now we only want there to be a 2.5% chance that we run out of DVDs, right? So here's the DVDs. We only want there to be 2.5% chance that we're going to run out. So basically, we're curious in what is this z-score so that we can find the corresponding x, which would be the number of DVDs. Huh, ain't that neat? So what percentage of the curve is left over here on the left? Well, if this curve adds up to 100 and this is 2.5, then this must be 97.5% of the curve. If only we could somehow figure out the z-score. Aha, but we can. We can reverse look up 975. So if we can find 0.975, then we can go figure out what that z-score is. Ain't that neat? Now, here's a caveat. Sometimes in these questions you can find exactly that like particular percentage on your table, and other times you can only get really close. Okay, I ask that you get as close as you possibly can. So I'll always be using the number that is the closest. So let's look up, reverse look up rather. So you see, these are the areas, right? So you gotta, this takes a little longer because you gotta go. And if you're a little dyslexic like me, it's quite hard, but oh, it just popped out at me. There's 0.9750. So I can go look up the z-score. That's a z-score of 1.9, and let's get the other decimal, 1.96. Represents 97.5% of the curve. Oh, great. So we reverse look it up. Eureka, we figured it out. So we reverse look it up, meaning we find the area on the table and then look up the corresponding z-score. And for that area, we got 1.96. Great. There's a picture that represents it. Now we can finally solve for x. So how do we do that? Well, we have this formula, right? And we know everything except for x. So we know that the z-score is 1.96. Don't know x, but they gave us the mean in the question. The mean was 100. And if you want to pause and go look up that standard deviation, it was 10. Now, you have to do a bit of algebra here to solve for x. I am quite kind. And I went ahead and put that on your formula sheet. So if you're ever looking for an x, like here's your z-score formula. If you're ever looking for the x value, you're going to go z times the standard deviation plus the mean. So if you do the algebra, that's what you're going to get. And I kind of thought, I'm not going to make this course about algebra. Like, you know, we already have like a bazillion formulas already, and we're in like week 4 or 5. You're just going to have one more formula. But if you know how to do the algebra, then, you know, more power to you. I realize that this isn't like a math course in the math department. This is a math course in the business department. So, anyways, so you can use this. Okay, but if you do it the algebra way, you know, you multiply both sides by 10, right? So that's the standard deviation over here times the z-score, and then you have to add 100 to both sides, and you're going to get this. So the work's going to be 1.96 times 10 plus 100. Give you a moment to calculate that, and you're going to get 109 or 119.6. Remember, these are packs. Now this is the real world, so you can't buy 0.6 of a pack. So you're going to have to round up. Even if I got 0.1, you'd be rounding up, right? Because it's suggesting you need 119.1 packs. You got to round up to be sure in the real world, right? So there you go. So store needs to buy 120 packs to avoid to have a 2.5% chance of not having enough, which is kind of neat if you think about it, right? Like, remember, let's just make sense of this, like just using some very like easy logic. Like they usually sell 100, and the standard deviation's 10. So remember, if you go out to 110, or if you go down to 90, that's 68% of the distribution. Now they only want a 2.5% chance. So if you go to another 10 DVDs, then you're at 120. And what's that? That's approximately 95 or 96% chance. So it's very close. It's very close. Every normal distribution looks different. So with those numbers, that's the way it works out. Now, this is my favorite. This is my absolute favorite. I love this. I love it. I love it. I love it. I'm going to make sure I'm still recording. Okay. Sometimes it randomly stops recording and it sucks. So, in certain situations, we can use a normal distribution to get reasonable answers for data that's actually binomial. This is awesome. The figure on the next slide shows several binomial distributions. Notice that as n gets larger and p, or probability, gets closer to 0.5, the graph of the binomial distribution tends to have a symmetrical bell-shaped form of the normal curve. So somebody noticed this. And remember, if the middle is 50%, then you're getting close to a normal distribution. So let's go ahead and take a look at these wonderful pictures. Now I circled the one that ends up being a normal distribution, but here's binomial with n equal 20 and a probability of 0.2. So it looks like a skew, right? That's like a skew. Look at this one, n equal 50. So big N, small p. It's this weird skew thing again. Big N again, and bigger p. Still kind of skew, but see how it's starting to shift towards the middle? Now, binomial with 50, n equal 50, and a 50% probability. That's really looking like the normal distribution. Now, I circled this one. It's just showing you that even with an n of 20 and a probability of 50%, you're already starting to see that normal distribution coming on. So some mathematician or somebody noticed this and they're like, well, there must be a way to approximate a binomial distribution using the normal distribution. Now, where does that help us? Well, remember how I said, you have those questions where you say it's a binomial distribution, and I say like, there's 100 trials, and I want to know the probability that like X is greater than 40 or something, right? Then you'd have to find the probability of 40 plus the probability of 41 until you get to 100. And if you're like, well, I'll just use the complement rule, well, you still got to go 1 minus all the cases that aren't there. That's a lot of cases. So if there's a way to approximate this binomial question using the normal distribution, that would be amazing. And it turns out there is. But in order to do it, there's a couple things that have to happen. So there's a couple checks that you need to make sure are the case or true before you can actually use the formula I'm going to show you. So when can we use this approximation? Well, in cases where the data is binomial, so probability of success like p and a probability of failure of 1 minus p, the following has to be true. N times p has to be greater than or equal to 5, and n times 1 minus p has to be greater than or equal to 5. If those two things are true, then you can approximate the mean by going n times p, and we already knew that from the binomial distribution, and the standard deviation by going n times p times 1 minus p, and then doing the square root of that. And we modify our z-score formula to have this correction factor of 0.5. Now, it's kind of like, a correction factor of 0.5. Does it make a difference? Well, it really depends on like how big the x value is. It depends on all sorts of stuff, whether or not it's going to make a huge difference. But the formula has this correction factor of plus or minus 0.5. Now, how we deal with that precisely, I'll talk about in a moment. Like right now. So let's go ahead and do this flipping a coin, a fair coin question. Okay, so we know flipping a coin is a binomial distribution, right? Either you get heads or you get tails. So suppose there's a binomial variable x where n is equal to 50 and the probability of success is 0.5. So, flipping a coin. Find the probability of x greater than 23 successes, okay, in the n equal 50 trials. So I could say, like, what are the chances of me getting more than 23 heads or something like that? Well, in a regular binomial question, I'd have to find probability of 24, 25, 26, all the way till I get to probability of 50. Even if I use the complement rule, I still have to calculate probabilities from 0 to 22, and that's like, that sucks, man. So, if you find yourself in a situation like that, where you're like, it doesn't seem like I can do the complement rule very easily, then check and see if maybe you can use the normal distribution. So we need to check these things right here. Is n times p greater than or equal to 5? Well, n is 50, and p is 0.5. So when you go 50 times 0.5, remember that's mu, well, you get 25. And that's greater than or equal to 5. So you put a check mark, so you pass that check. You also must pass this check. So is 50 times 1 minus p, so that's still 0.5, is that greater than or equal to 5? Put a question mark. Well, yeah, it is. You get 25 again. So we can use the normal approximation. If we're going to use a normal approximation, then we can use the formula that I mentioned before. Now, a couple page flips behind here. We calculated the mean, but we need to know the standard deviation, right? Now, that formula was this one here. I'm going to do my best. N times p times 1 minus p. So plug in your numbers. Well, now n times p is 25, so we'll save ourselves some time. 1 minus p is 0.5. Type that in on your calculator, and then do the square root of it. Pause the video for a moment. You get 3.5355. Great. So we got that for our standard deviation and this for our mean. So remember that as we go to the next page, which is completely blank. Now over here, I've written my formula, just to remind you. And I'm just going to rewrite our data. So we got our mean of 25 and our standard deviation of 3.5355. Now, we're looking for a probability that x is, greater than 23. Okay. Now, how do you deal with this correction factor? Well, let me write over here. The correction factor must be chosen. So it must be chosen so that, well, in this case, x is greater than 23. So that x is greater than 23. We need to make sure that we do not include the number 23, right? It says x greater than 23. Now the correction factor is either add 0.5, so 23.5, or subtract 0.5 from x. So out of these two numbers, which one, if you did greater than, would ensure that you don't include 23? So if I did x greater than 22.5, then that would imply that I'm including 23. So that is not the right number. Now, if I choose this as my number, 23.5 is clearly bigger than 23. So I'm going to be sure that x is actually greater than 23. And that's how you figure out the correction factor. I know it's a little weird. It requires some thinking. We'll do a couple more problems where all we do is figure out the correction factor because it's a big deal. If you don't get the right correction factor, you will lose marks, okay? So, and I get it. Like sometimes if the numbers are big enough, it hardly makes a difference. But the thing is that if the numbers are small enough, it can make all the difference. Remember, this is an approximation. So the formula has this correction factor for a reason. It's there for a reason, okay? It is important. So here we go. So for my x value, I'm going to use 23.5. And then it says subtract the mean, which is 25, divided by the standard deviation, 3.5355. So now I can find, this is my z-score, right? Get the z-score. What does it end up being? Negative 0.42. Cool. Now, be careful because we're looking for x greater than. So when you draw your normal curve, and remember, this is a necessary step. I'm getting better at drawing it. Remember, this is z equals 0. Okay, and this is the mean, and I'm looking for x greater than 23. So this is the mean of 25. Now I landed below. Doesn't matter where I draw this, but this is x, and I'm looking for greater than 23. So I found the z-score of negative 0.42. But which way am I looking? Am I looking for the area to the left? No, it's x greater than 23. So I want to know this probability. So I'm looking for the area to the right. Here's a pro tip. In your question, if it's greater than, it's always the area to the right, right? And look, the greater than sign even points to the right. If I was looking for x less than 23, I'd be looking for the area to the left. Very important distinction. So go to your table, and we now know that the probability that x is greater than 23 is equal to the probability that the z-score is greater than negative 0.42. I will be looking for this line in your work. You must include that line for full marks. Let's go look it up. So look up negative 0.4, and then scroll over till you get to the 0.2 column, which is this one here. There it is, 0.3372. This table gives us the value to the left, so I'm going to have to go 1 minus that. So here we go. Probability that z is greater than negative 0.42 is equal to 1 minus probability that z is less than negative 0.42. And that was 0.3372. which gives us an answer of 0.6628. Excellent. So what does it mean? There's a 66.28% chance of more than 23. Now, I was using the word heads. The question didn't actually say heads, but of getting more than 23 successes is what it said. Okay? Now, some of you might be wondering, well, if I did this question using the binomial theorem, and I just calculated probability of 23, 24, 25, all the way up to 50, and added them all up, would I actually get close to 66.28? Because remember, this is an approximation, so it won't exactly be the same as using the binomial, but it should be pretty dang close. Well, I went to my favorite calculator, and I went and found out the actual probability. So if you flip a fair coin 50 times, what's the probability of getting more than 23 heads? So sequence of coin flips, greater than 23 with 50 flips. Check out this probability. 66.4. Here's a normal distribution. We're looking for the area to the right, so it's highlighted in red. 66.4. What did we get? 66.28. We are pretty dang close using this approximation. Yeah! Woo! It's amazing. Okay, so it works. The normal approximation method works. You must have all this work, okay? So I said that we would take a look at doing some more calculating it's called the continuity correction, so that plus or minus, right? So the plus or minus in the formula is the continuity correction. So what I have here, there's a bunch of blah, 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 blah. You can read it if you want, okay? There's like another example embedded in here, so if you want to read through it and kind of really read the logic, you can. You're more than welcome to pause the video. However, my logic is a lot more simple and a lot less wordy. I'm a man of few words, I have a math major. So here we go. So let's say that the binomial probability is, let's start with this one down here. Okay, let's start with the single ones before we start doing a range. So what if I want to find the probability that x is less than or equal to 27? Well, what our textbook suggests is, well, write out all the probabilities that would be included, right? So that'd be 0, 1, 2, 3, all the way up till you get to 27. So we need to include 27. So with the continuity correction, we got to go to x less than or equal to 27.5. Why? Well, if you're going less than or equal to 27.5, then you will definitely include 27. And I know that's confusing, but think of it this way. This needs to have 27. You have two options. The continuity correction says you're either going to go 26.5 or you're going to go 27.5. Now, do you want x to be less than or equal to? Plug in this number. If you go 26.5, Will you be including 27? No, you will not. So that's not the answer. This is the answer. That's how I do it every single time. Okay? There's lots of ways to think about it. I have found over the years of teaching, the easiest way is to write out your two options and see if it fits into what you're originally looking for. Okay? Let's do this one here. Why don't you pause the video and try it out yourself and see if you get the right continuity correction. Okay? So, x is greater than 30. So my options are, with the continuity correction, 30.5, or I could do x greater than 29.5. Look at this. Does x greater than 30, does it include 30? It does not include 30. So if I go x greater than 29.5, well, that would include 30, wouldn't it? Because I'm going greater than 29.5. So that is not the continuity correction. This is. And there's the answer. Are you getting it? I hope so. There are another two. Now, what's the difference with these ones? The difference with these ones is you're going to be doing two continuity corrections. Okay, so there's really nothing special except that you're doing the same. You're doing it twice. Okay, let me erase all of this. So I'll do A. Ooh, I can just highlight it and delete it. Oh, now it's not selecting. Of course. You know, I gotta say PowerPoint ain't the best for this, but whatever. I have to keep going back. I don't know if it's just me or what. Okay, so let's look at, say, this one first. So this one is x greater than, now remember, when you're reading it backwards. So this is probability that x is greater than 25. So what's the continuity correction? Well, you can go 25.5 or 24.5. You want to be greater than 25. So not actually including 25. So if I go x greater than 24.5, then I am including 25. So that's not the correction. It's going to be this. So look over here. They're actually going to be doing 25.5. Okay, get it? Look at this one. This one's x less than or equal to 30. So two options, 30.5 or 29.5. Now, if I want x to truly be less than or equal to 30, am I including 30? The answer is yes. So if I were to go x is less than or equal to 29.5, did I include 30? Nope, I did not. So I need to pick this one. Boom. If you do it that way, you know, it takes an extra 30 seconds, but you'll always have the right continuity correction. And that's the DeMuro method. Oh boy. Another question. Now, this question is absolutely bonkers. Absolutely bonkers. So what I'm going to do is say, hit pause and maybe read through it. It's a big question, you know, and these are the examples that are found in your textbook. Some of them are like way too wordy. So whenever you have a question that has to do with kitty puke, you know it's that I took the concept and made the question, took a different question to make it easier. Yeah. Okay. I will read through it so you can fast forward. Food processing company markets a soft cheese spread that is sold in a plastic container with an easy pour spout. Although this spout works extremely well and is popular with consumers, it is expensive to produce. Companies don't like that. Because of the spout's high cost, the company has developed a new, less expensive spout. While the new, cheaper spout may alienate some purchasers, right? Some people are going to be like, I don't like this cheaper thing, and try to find a similar product somewhere else. A company study shows that its introduction will increase profits if less than 10% of the cheese spread's current purchasers are lost. We're happy to lose you as long as we make more money. That is, if we let P be the true proportion of all current purchasers who would stop buying the cheese spread if the new spout is used, profits will increase as long as P is less than 0.1. Suppose that after trying the new spout, so now they're doing an experiment, 63 out of the 100 randomly selected purchasers say they would stop buying the cheese spread if the new spout was used. To assess whether P is less than 10%, we will assume for the sake of argument that P equals 0.10, and we will use the sample information to weigh the evidence against this assumption and in the favor of the conclusion that P is less than 0.1. Let the random variable x represent the number of 1,000 purchasers who say they would stop buying the cheese spread. Assuming that p equals 0.1, then x is a binomial random variable with n equal 1,000 and p equal 0.1. Stop there for a second. Is this a binomial experiment? Yes, because either you stop buying the product because you don't like the spout, or you continue buying the product because you like the spout or you don't care about the spout. Okay, but anyways, there's two outcomes. Since the sample result 63 is less than mu equal n times p, so what are we doing here? 1,000 times 0.1. We're checking to see if this is bigger than 5, to see if we can do the normal approximation, right? So it's equal to 100, so it is greater than or equal to 5. So the expected value of x when p equals 0.1, we have some evidence to contradict the assumption that p equals 0.1. To evaluate the strength of this evidence, we calculate the probability that 63 or fewer of the 1,000 randomly selected purchasers would say that they would stop buying the cheese spread if the new spout was used if, in fact, p equals 0.1. Whew, that's a lot. What the hell are we doing here? Let me sort of make it a little bit... Well, let me talk about it for a second. So, what are they saying here? They're saying, like, okay, if you go 63 out of 1,000, what do you get? Get 0.063, I should know. So, is this number truly less than 10%, right? Remember, if we lose 10% of the people, then we're actually going to make less money, even though the spout costs less to produce. Okay, so what they're saying is like, well, we know there's a standard deviation here. We only asked 1,000 people, right? So even though this proportion is less than 10%, we want to be extra sure. So we're going to do a normal distribution. We're going to normalize the data, okay, because we can find the standard deviation for this situation. We're going to normalize the data and really make sure that the true proportion of people who are not buying it is x is less than 63. Let's say less than or equal to 63, right? But 63 people or fewer. So they're basically asking, what's that probability? Well, it's a binomial question. We can use a normal approximation most likely because this is greater than 5. So what are we looking for? We're going to be looking for that z-score, right? Looking to see if that z-score, once we normalize the data, is actually less than 0.1. Okay? So there's a bit of work here. They basically are showing that, n times p is 100, and then n times 1 minus p is 900, and those are greater than or equal to 5. So we can use the normal approximation. Okay, and then they go and they calculate the standard deviation of 9.4868. So now we have everything we need to do this question using the normal approximation. And I know it was really wordy, but I just wanted to show you a question that, like, might come out of the real world, okay? Because it's never this nice little, oh, here's all the data in 2 sentences, off you go. Like, it's always going to be a complicated situation, and you got to think about it. Now, the purpose of this course is not to give you these novels and for you to figure it out. The purpose of this course is to get you used to the calculations, and then hopefully with your business knowledge, you'll be able to know what to apply. So, let's go for it. Let's do it. Let's do the math. We're here to do the math. So again, I wrote the formula here for your benefit, and we calculated the mean to be 100, and the standard deviation was calculated for us, although I could easily ask you to calculate it, given the data in the question. And we know that we're looking for the probability that x is less than or equal to 63. Now, because we're using the normal approximation, we have to take that moment to be like, here's our 2 correction factors. Now we want x to be less than or equal to 63. So that includes 63. So if I go x less than or equal to 62.5, will I be including 63? No. So I need to do this. I need to use 63.5 because that would actually include 63 when I go x less than or equal to that number. So z equals 63.5 minus the mean of 100 divided by the standard deviation 9.4868. Whew, what do we get? Well, plug it in on your calculator. And now this one's interesting. You get negative 3.85. Now remember, draw your picture always. Normal distribution. Z-score of 0. In the real world, that's the mean of 100. Now, we want less than 10%. So we want the true proportion of people to be less than 10%. So whatever z value we got, now we got negative 3.85. When we look up because it's x less than or equal to 63.5. We want the area under the curve to be less than 0.1. So when we look up the probability that z is less than negative 3.85, we want that probability to be less than 0.1. Now, here's two things that are happening. You need to realize that this is the test. So we need this to make the cheaper spout profitable, right? Because we're going to lose customers if it's greater than 10%, okay? You need to go look up this value on your table. Now, some of you may have started doing that, so let's take a look. Where's that table? Here it is. So, negative 3.85. Well, our table only goes to negative 3.39. And look, what's happening to the probabilities? It's tiny, right? So if you look up negative 3.39, is that less than 10%? It's 0.0003, okay? If you go find 10% approximately, where are we here? 10% approximately, can we find, this is about as close as we get. So the z-score of negative 1.28, any z-score less than negative 1.28 would be low enough. Okay, so you would say in this case, you say since probability that z is less than negative 1.28 is approximately 0.1% of the curve, probability of z less than negative 3.85 is less than 0.1. So therefore, what's the conclusion here, right? Like, can they use a new spout or not? So therefore, they can use the new spout. Boom. Now, that is a hard question. I just wanted to demonstrate to you a question that's really using the stats in sort of a real world context. So I apologize, it's very long. Is it possible to calculate this z-score? And the answer is yes. Like, we have a finite table in front of us. The normal curve is infinite, right? Remember, I said that curve is infinite. So while the probability adds up to 1, we can theoretically calculate any z-score. So I went ahead and did that. And I just typed it in here. And probability that z is less than this is right here. So it's 0.00005. So it's like orders of magnitude less than 1%. Okay? Neat. So, still recording? Excellent. What's next? Exponential distribution. Now, I'm going to do some fill in the blank. And then for the rest of this, because I don't often give questions on this, on tests and things. I might do it on like an open book thing or like in one of the labs. I give questions on Poisson distribution. Those you can expect. I give questions on rectangular distribution. Exponential we cover. We might have it in an assignment, but it's not going to be on like a midterm or final. Okay, so what is the exponential distribution? Suppose that some event occurs as a Poisson process. So I said it has something to do with the Poisson variable, Poisson process. That is the number of times an event occurs in a Poisson random variable. So let x be a random variable of the interval between successive occurrences of the event. Then x is an exponential distribution. Now, it is very tricky to spot the difference between this and a Poisson distribution. Now, remember, Poisson variables model the number of arrivals in a fixed time frame. Right? So remember, there's a fixed time frame if it's a Poisson variable, which is a discrete, such as like a number of cars per hour in a road kind of thing. Okay? So if I say, hey, there's like 5 cars per hour go by my house, I live out in the country. That's a Poisson random variable. Exponential distributions model the time elapsed between consecutive arrivals, which is the continuous data, such as how long after one car will wait until we see the next car on the road. Let's stop. So the Poisson distribution would be like, hey, there's 5 cars per hour on this road. The exponential distribution would model, okay, there's 5 cars per hour on the road. How much time passes between one car and the next car when we have 5 cars per hour on the road? Why do we need to know this stuff? Who the hell knows? There's got to be a real world application of it. Whether or not we get that far, in this course, we ain't gonna. So, at this point, for the rest of it, I'm going to say read through it on your own. I have a question that has all the numbers plugged in, okay? And it might show up on a lab or something like that. It is on your formula sheet right here, okay? Here's the Poisson distribution. Here's the rectangular distribution. It's all there. I'm a nice guy. But you're on your own for this one because it would literally be just me reading off the slides. Okay, like these questions are very much like plugging in the numbers. Okay, it's using Euler's number again. Okay, so Euler's number is in the formula. Read it on your own, try it out, and there may be like one question on the homework, I think. Here's the summary. Very good summary. Suggest you read it. Do your homework, my people. I will release another video with just examples. Less talking, more examples. It was a long one this week, but there's a lot of slides. So, be good, do your homework, and stay safe. Goodbye, everybody. Bye-bye.